Good morning, Year 12s. So my name is Cherry. I'm reporting on behalf of Team Switzerland. I will be presenting problem number 7, Bead dynamics. So the problem statement is, a circular hoop rotates about a vertical axis diameter. A small bead is allowed to roll in the groove on the inside of the hoop. Investigate the relevant parameters affecting the dynamics of the bead. And then the setup includes a circular hoop and a vertical diameter, and the task is to investigate the relevant parameters. So when the hoop rotates, the bead moves away from the vertical axis and travels up the hoop, where it oscillates around an equilibrium position. This is my experimental setup for measuring the equilibrium position of the bead. So my phone is clamped by a clamp to record like a video, and then from the video I track the equilibrium position of the bead. And then the metal tube here is to ensure that the hoop is rotating on a vertical axis. So now I'll talk about my theoretical analysis. Here are the forces. There are 3 forces, the normal reaction force, the gravity force, and also the friction force, which is not here, because first I'm not going to investigate the friction force. And so this is the spherical polar coordinate system, which I'll be using in my investigation. The radius of the hoop, the r represents the radius of the hoop, theta represents the angular displacement of the bead, and phi represents the angle displaced by the hoop. And the rate of change of the phi component represents how fast the hoop spins, so basically the angular frequency of the hoop. And so for all spherical polar coordinate systems, this is the acceleration. Like I didn't derive this, it's just from like a textbook. The net force equals the mass times acceleration by Newton's law of motion, and it also equals the gravity force plus the normal reaction force, because I'm not investigating the friction force just yet. And then so now I will only be looking at the theta component, because the r component stays constant because the radius doesn't change when it rotates. And then also the phi component is the rate of change of the phi remains constant because the angular frequency is kept the same during the rotations. And so when the bead reaches a equilibrium position, the net force equals to 0, because according to Newton's law, if it doesn't move, there is no force. And then so from this equation, we have 2 solutions. Either theta equals to 0, which makes sense, because if it's at the origin, then the bead doesn't have any angular momentum and it will just stay there. And then, or theta equals to arc cos 1 over beta, where beta represents the centripetal force, the ratio between the centripetal force and the gravitational force. And then, so on the diagram here, we see a plot of beta, the ratio, versus the theta, the angular displacement. And as you can see, when the angular frequency is quite small, the bead stays at the origin, and when it gets bigger, it increases, and it eventually diverges to pi over 2. And here, there's clearly a change in the phenomenon. This is because there's a critical frequency here, which I'll discuss later. This is a graph comparing theoretical data with theoretical and experimental values. As you can see from the graph, it is a very accurate prediction, because the theoretical line, the black line, clearly crosses the error bar of every single point. However, in the later half of the graph, you can see that all the points, all the plots, are actually slightly above the curve. This is because I neglected the friction force. So back to the critical frequency. This is when the angular frequency equals the critical angular frequency, and this is when beta equals to 0. So the so the centripetal force equals the gravitational force, and so we derive this relationship for the critical frequency, which equals the root g over the radius of the hoop. And so in order to generalize the angular frequency in relation to the critical frequency, we can introduce some new constants. So k, you can see k here represents the square of angular frequency divided by the square of critical angular frequency, and tau here is to relate the critical angular frequency in terms of time, and then this is theta prime is to relate the rate of change of the angular displacement in terms of the critical angular frequency as well. So, in order to establish a phase plot, we need to establish a relationship between theta prime and theta. So if the theta prime equals the critical relationship equals the critical angular frequency squared times theta dot, as we discussed earlier. And so if we substitute this into the equation of motion, we get this equation at the bottom of the slide. This eliminates radius as a parameter, and the only parameter here is the k, which is the angular frequency in relation to the critical angular frequency. So now, if we integrate this equation of motion, we find the equation at the bottom of the slide. And this shows the relationship between theta and theta prime. So the angle and the angular velocity. And the term A, after you study integration, you see that this is basically the C constant, so it represents the initial displacement of the bead. And so I used Mathematica to plot the relationship I derived earlier, and here are the phase portraits. So you can see that when the angular frequency is smaller than the critical frequency, there's only one equilibrium position, and it's at theta equals to 0. So that means it oscillates, and then it comes back to 0, just like I predicted. And then this is about the same. And then this is when the angular frequency is bigger than the critical angular frequency. There are two equilibrium positions. This is because the hoop is symmetrical, so you can have 2 points on either side. And then it's not at 0. Okay, so now we talk about damping, which basically means there's a resistant force, and in this case it's air resistance. And the damping term would be this, which is proportional to the velocity and a constant b. So also I used Mathematica again to plot these graphs. From this graph, you can see that when it's smaller than the critical frequency, it oscillates again towards 0, the x-axis. And then when it's bigger than the critical frequency, it oscillates around the equilibrium position it later reaches. And then, so now we can talk about the dynamic model. So we can, instead of just the equilibrium position, we can look at how it changes as it starts to rotate. So this is the equation of motion in relation to theta instead of theta prime. Here is a graph comparing my theoretical measurements, my experimental measurements, so the black plots. And the blue line is the theoretical model. And you can see the pattern is clearly the same. And these are the phase portraits that show the relationship between the position and the velocity. The different lines represent different initial positions, so the A constant we talked about earlier. And so you can see same with this, when it's smaller, it spirals, it oscillates, and it goes back to theta equals to 0, so the origin of the hoop. And then when it's bigger, it oscillates, but then it goes to like a equilibrium position that's not the origin, that's on the side of the hoop. However, when I was conducting my experiments, I realized that the vertical axis is not always in the middle. So like I fixed the hoop by like attaching it onto a metal rod, and the holes were clamped by a clamp stand. I'm not sure actually. And then so I realized that the vertical axis is not always in the middle. So now I'll discuss the asymmetric case. With the asymmetric case, the radius is not always the same. So if you're here, it would be r plus d, or like the line between here and here. But when you're here, it's like clearly shorter than the r. So that means the centripetal force would be different, and so the beta would be different because it's the ratio between the centripetal force and the gravitational force. And so the constant alpha is the relationship between the deviation from the vertical axis to the radius, and we can derive a new relationship for beta. However, this also holds true for the first model we derived earlier without the friction and without the deviation from the hoop, because if the deviation is 0, then alpha would equal to 0, and also if we neglect the friction, the coefficient of friction will be 0 as well. So then you can eliminate some of the terms that includes mu and alpha, and you end up with the same relationship. And here's another setup I used to measure the asymmetric case with an electric motor and a light bearer. This is to measure the angular frequency of the hoop, and this is a power source. Here's a short clip showing the movement of the bead when the hoop is symmetrical. As you can see, now it's on the shorter side of the hoop, and it slowly moves to the vertical axis. It's a bit slow, I'm sorry. And then, so now it's on the longer side, and it clearly moves faster, and it's going to reach an equilibrium position around here. Using Mathematica again, we plot a graph of beta versus the angular displacement for the asymmetric case. They're not symmetrical because the two sides of the hoop are not symmetrical. And clearly, if you have a hoop, it's not gonna. There are two different equilibrium positions for angular frequency larger than the critical frequency, and then when the bead travels from the longer side here, it quickly moves to the on the other side. And here is a graph of the measurements for the equilibrium position, and the plots clearly cross all the theoretical line. And so I would say that my model very accurately predicts the phenomenon. From the new equation of motion using Mathematica again, we can model the trajectory of the bead. This is when the angular frequency is smaller than the critical frequency. It oscillates around where it started, and then also same with when it equals the angular frequency. And then this is when it's bigger, it oscillates around a new equilibrium position like the symmetric case. In conclusion, the parameters I investigated include the angular velocity at the initial displacement, and for the symmetric case, I looked at the equilibrium position, the frictionless dynamics, and the dynamics with damping. And so for the generalized case, I looked at the equilibrium position and the dynamics. Oopsies. And so here are the sources that I use, and thank you for listening. Do you have any questions?
Patrick. Yeah, so first of all, congratulations. It seems very impressive. And second of all, how long did all of this process take?
So I also did this for my extended essay.
Oh, okay.
So it was a very efficient use of time because I also used for my extended essay, but I didn't use all of it for my extended essay because some of it's like too far off the syllabus. But also, so after I got qualified for the national team, I went to Zurich for a month to a Zurich high school called MNG, and basically they only study science and math there. And then I did another month of training, and I finalized the presentation there.
Was that during the school year? Yeah.
June. Yes.
Great.
So I imagine a lot of the Year 12s here are sitting here thinking, that seems like a big project and overwhelming. What were your first steps? So if they wanted to simulate, what would you advise is the first thing you should do?
So first, what I did was I looked up videos of this problem on YouTube, and you can find a lot because the Canadian team, for some reason, they always publish videos on these problems, and that was very helpful because, well, this looked interesting, so I picked this problem, and then and then I moved on to reading literature papers, and then yeah, that was it. And then I had like a theoretical prediction, and then I also Mr. Earl helped me a lot with my experimental setup, and then we did some data collection. So yeah. Yes.
Can you tell us a bit more about how the competition worked? So you've done very well in the Swiss competition and the international one. What's the format of that? What's the how did that work? What were the scary bits?
For the national one, it was online, so it wasn't that scary. He was also in the national one, so he can also tell you about it. And then for the international, it was really scary because we went in person, and it was in like a weird university. It was in Georgia, Kutaisi, and there was like nobody there because it was like a little town. It wasn't even a city, and it was like a newly built university. And for every round, basically you have like physics fights, and every fight is like 3 rounds. So either you present the problem, or you oppose someone else's problem, or you review people's debates, and then every round you switch. And then for every physics fight, you are in the same room with 2 teams. So for example, when I presented this problem, I was with Austria and Czech Republic. And I think it was Austria who opposed me, and it did not go very well, so yeah. It was very scary. Yes, sir.
Jerry, tell us about the teammates on the Swiss team, and did everything happen in English?
Most of it was in English, but when we were in the high school, all the teachers spoke Swiss German. So I learned of Swiss German, but I cannot, yeah.
And what about your other teammates?
3 of them were from Zurich, and 1 of them was from England for some reason.
And you spoke English to each other?
Yeah.
Yep.
Yes.
So, Joe, for your competition, you have to do 3 problems. Can you just tell us briefly what the other problems were that you had to investigate?
So the second problem I investigated was called fuses, and you basically look at how the power, or like how the diameter of the fuse, or like how the length of the fuse affects how long it takes for the fuse to blow up. It was so fun, and I burnt myself a lot. And then my third problem was called Invent Yourself, and it was you have a boat, and then there's like an oscillating pendulum here. It moves around, and the boat, you know how like if it's oscillating, the boat will move like that as well. I basically modeled that.
So a design and build, an electricity one, and a mechanics one.
Yeah.
So 3 different disciplines. The other question I've got is relating particularly to your presentation here. It's, obviously, the maths of this takes some interpretation. If we were thinking of a fairground ride,
What?
A fairground ride where you're going to be spinning around a thing. Can you just tell us what we would expect? How would we expect to move if we're on one of those swings that goes round a fairground ride? What does your investigation tell us about our motion? Is it as a short sentence? If we get on there and we start spinning, how do we expect to be moving?
I think the change in the angle from the vertical axis should be the same with what I predicted, because the angular frequency is constant, and then the radius is constant. Yeah, so it should be the same. It would oscillate, and then it would stay
And would
the
it
same.
affect how heavy you are?
No. Mass is not. It would affect how long it takes for you to reach equilibrium, but it would not affect the position.
I see. So no matter how heavy you are, you'd end up at the same angle on one
Yes.
of those Vogt numbers.
Because when you sit next to an empty one, it's also at the same height.
Okay.
Yeah.
So good observation.
Yes, Vanessa.
So you said if you had those 3 problems, then what made you like go further with this one? I guess. Like, did you do all 3 for the international competition?
Yeah, I only did this one for the national one. And then once you get selected, they make you do 2 more.
Oh, okay.
Yeah.
How long did you have to answer each of the questions you asked, like in that international competition?
You're allowed 12 minutes to present a problem, and then you have to ask questions for 10 minutes. That's the worst part. And then if you are reviewing the problem, it's 4 minutes, I think. I'm not sure.
How long did you have to prepare your other solutions? Obviously, that one took you months. How long did the other 2 problems? How many hours or weeks did you have to prepare the other 2 problems?
It was much quicker because I was just in the high school every single day, and it was like a week, and then the one problem was done. But it was like from 9 o'clock in the morning to 9 o'clock at night.
So like a heavy EE week.
Yeah. Yes, sir.
So we've heard that you use this to support your extended essay. You've represented Switzerland at a national level. Where next, Jerry? What's the next step?
I don't know. Hopefully in university somewhere.
And did you use this as part of your application?
Yeah, I submitted it as an attachment, but I didn't really talk about it.
Good to know.
It features on Chevy's UCAS form.
Oh yeah, for my UK one, yeah.
So it's very good, I say this to everyone, when you're writing your personal statements or your transcripts, you want to have something more than I have been at school studying physics the last few years. And something like this is a very, very powerful extra addition which will really catch someone's eye. Even if you don't get up to the international sort of the finals, having entered the competition on its own and said I did this, makes someone go, this is someone who's interested in my subject, I think I'd like to have them on my course. So it's something to bear in mind.
And I can't believe this won't be a big part of the conversation at Cherry's interview next month.
Yeah.
So well done for providing an audience, give her a chance to rehearse it again.
What they ask about it?
Sorry?
What they ask about it?
I would.
So do you have any more questions? Okay guys, I think a final round of applause to Cherry.